Next speaker is Professor Phil Chodrow, a faculty in the Department of Mathematics at the University of California, Los Angeles. So he has been recently pioneering exciting work in the intersection of network science, nonlinear dynamics, and machine learning. And today he's going to talk about clustering in hypergraphs. So over to you, Phil, and thanks a lot for joining us.
Hi, Drew, and thank you for the really generous introduction, as well as the opportunity to be here today. This is a new venue for me, so it's a real pleasure to get to learn from the speakers who are here, and I'm looking forward to taking what I've learned here and building my own understanding, and hopefully doing some cool new things with this inspiration. So what I'd like to do today is share with you some very recent work, hot off the presses, on generative hypergraph clustering through a modularity-based lens. So this is a topic that there was kind of this fortuitous coincidence, because I know that Tarun, among others in this room, has in fact worked on this topic. And so when I received the invitation to present here, I thought this was a really exciting opportunity to share what we've been doing and get some new perspectives and feedback on this work. So I'm really grateful for the opportunity. The work I'm going to present today is joint with Nate Velt and Austin Benson, both at Cornell. So here they are, and so Nate is in the math department at Cornell, Austin is in the computer science department at Cornell. Y'all, Nate is on the job market. So if you're here, if you're on a hiring committee in computer science or applied mathematics, then Nate is awesome. 7 out of 5 stars, highly recommend him, hire this guy. So just a little shout out for him there. This has been a fantastic team to work with, and I'm so grateful for their partnership and skill in putting this all together. So with their help, here's the preprint that we just put out just a few weeks ago. Generative hypergraph clustering from block models to modularity. Later on, I'll post in the chat during question time a link to this if you want an easy access. Okay, so what are we doing here? This is a very low-tech kind of task in some ways. I'm talking about graph clustering first. So graph clustering is a fundamental problem when in network science, the analysis of networked systems that might be physical or information-based or anything else. So in the basic graph clustering problem, what we want to do is take a graph like the one that we see there on the left, and then observe that certain sets of nodes in this graph are more densely interconnected or more closely related with each other than are other sets in the graph. And so we'd like to label these sets of related or densely interconnected nodes in some way, thereby partitioning the graph into, hopefully, meaningful groups. This is a classical kind of dimension reduction. We've seen it in applications to social network analysis, healthcare, various kinds of omics and bioinformatics. The list goes on and on and on. Of course, this is not the only good learning task on graphs. We've had lots and lots of speakers now telling us about lots of other things we can learn about graphs. But this is a very simple and very classical one that has inspired a lot of work for different methods to do this. So I like to think about hypergraphs. So hypergraphs are natural generalizations of graphs. Graphs relate pairs of individuals or nodes. On the other hand, hypergraphs contain edges or sets that contain more than 2 agents. So here's a picture of a graph. I actually stole this from the Wikipedia page for simplicial complex, but simplicial complexes are a certain species of hypergraph. So we can see in this visualization that we have edges that join 2 nodes together. We have edges that join 3 nodes together. Those are the triangles. And we even have a tetrahedron there. So that's an edge that joins 4 nodes together. So we can model interactions between sets of agents of arbitrary size. This is a good thing to do because many of the real systems we care about have what are trendily now called higher order interactions, namely interactions between 3 or more entities, that we can helpfully model with hypergraphs. So here's a graphic that Nate made, so thank you, Nate. We might use hypergraphs to model groups of people attending events. So in this case, an edge might be an event, and the nodes in that edge would be the groups of people in that event. We would see browsing sessions, for example. So maybe an edge is a browsing session online, and the nodes are the websites or product listings that you all visited jointly in that browsing session. Drug combinations, an edge would be a drug or a medical product, and the nodes would be the compounds contained in that combination. Or maybe you're going shopping, your edge is your shopping cart, and the nodes are the items contained in that shopping cart. So all of these are very natural cases where we'd like to model higher order interactions, and hypergraphs give us a very natural way to do this. So this brings us to a very natural question. How can we cluster hypergraphs in the same way that we can cluster graphs? And the particular flavor of this question that I want to ask today is, how can we construct specifically interpretable and scalable objectives for hypergraph clustering? So I am a math guy, and so I think a lot about the interpretability of objective functions and their connection to other mathematical concepts. So that's why my emphasis is there. Of course, other good emphases are possible as well. So I don't want to disparage other approaches. For today, what I'm really interested in is interpretability and scalability in these hypergraph clustering objectives. So I told you that I was going to propose a modularity-based framework. So let's say a bit about what that is. Modularity maximization is an extremely common and perhaps even the most popular method for clustering graphs in the network science community. So the paper that introduced modularity maximization for finding networks has now been cited almost 14,000 times. So the modularity objective is a pretty simple objective to define. We consider the objective to be a function of the label vector z. Z contains a label for each node. So the ith element of z tells you the label of node I. What we do to compute the modularity is we sum up over all the pairs of nodes such that the two nodes share a label. So that's what that delta function at the tail of the sum is doing. It's restricting the sum to nodes that share a label. We're going to sum up over all the nodes that share a label. And what we're going to sum up is this quantity where we take aij, that's the observed number of edges between those two nodes. And a binary graph, that would be 0 or 1, but you can also do this for multigraphs. We're going to subtract from the observed number of nodes this quantity gamma, where gamma is a scalar, times this product term proportional to the product of the degrees of those two nodes. We often think of gamma as a resolution parameter that governs the sizes of the clusters that you get with modularity. Larger gamma will tend to favor smaller clusters. Smaller gamma will tend to favor larger, fewer clusters. So this is a mathematical objective function. And then the modularity maximization task is to find a label vector z, combined possibly with a good choice of the resolution parameter gamma, such that we achieve a high value of this modularity score that leads us to good clusters, where the notion of goodness is really up for a lot of debate and is subject to a lot of discussion. But this is the modularity maximization task for graphs. Now, there are both great things about modularity and really problematic things about modularity. So some good things about modularity are that it is highly interpretable in a number of different ways, and it's a really good playground for mathematicians like myself. We can derive modularity in a number of different ways. We can derive it by comparison to a random graph null model. This is the original formulation of modularity, actually. We can derive the modularity objective as an expression of the stability of a diffusion process on the graph. So there's a dynamical interpretation through the idea that a cluster of nodes should be one where it's hard for a random walk to escape. This is a nice interpretable definition as well. An interpretation that we're going to see a lot of later today is in terms of the block model likelihood. So in two relatively recent papers, groups independently showed that the modularity objective is an approximation of the likelihood of a function of a stochastic block model. So we'll see a bit more on that shortly. And then finally, there's another interpretation that I really like. I liked it so much that apparently I put it on the slide twice, which is the notion that modularity is actually analogous to a surface tension for graphs. So in addition to this great scalability going on here, or interpretability, there's also scalability. So there are pretty fast heuristics for computing high modularity partitions. So there's this greedy Louvain algorithm from 2008, which can be used to handle very large instances, as well as more recently, some nice approaches based on belief propagation that can also scale very nicely. And I'm sure I'm leaving some out here as well, so feel free to let me know offline if I'm missing your favorite modularity algorithm in here. So we have some nice notions of interpretability and mathematical connections, as well as scalability to large instances. However, there are also major issues with modularity that I don't want to underplay. Modularity is prone to both underfitting and overfitting, depending on your context, and this needs to be controlled in some way. Additionally, the modularity optimization problem has its own issues. It is NP hard, and so one is never confident that one has in fact globally optimized the objective. The landscape for modularity is also highly degenerate. So there are many, many, many local optima, some of which may be highly uncorrelated. So without trying to sweep under the rug the issues of modularity, today we're going to be trying to extending some of the virtues, and then I think the issues and problems associated with it are great points of further exploration here. This next slide is my tentative answer to the question of how can I annoy the most people in this workshop simultaneously. I wanted to situate the modularity maximization heuristic in the context of other graph clustering approaches. So here I've mapped out several graph clustering approaches that are on my radar and sort of located them roughly where I think they go on the scale of the scalability and interpretability. So generative inference is highly interpretable, but has issues scaling to even medium-sized instances. Lots of algorithms, infomap and spectral clustering have nice objective functions that are a little bit more scalable, but maybe sacrifice a bit in terms of interpretability. Modularity maximization is highly scalable, and as I've argued, it's getting more interpretable as people come up with more derivations and interpretations of it. I've also seen recently some work on graph neural networks that are for this clustering task that are highly scalable. I don't really know what the state of the art there is on interpretability. If I have left off your favorite algorithm, if I have mislocated your favorite algorithm on this graph, then please feel free to let me know. I'm always up to learn something here. That said, modularity is attractive because it's both scalable and, again, it's moving up in the world of interpretability as well. So those are some of the things to like about it. So what do I want to share with you today? I want to share with you a derivation and application of a scalable modularity objective for hypergraphs. So the idea for how we're going to do this is we're going to define a moderately realistic generative model. So this is a generative framework at heart. From that generative model, we're going to approximate the log likelihood to obtain a family of hypergraph modularity objectives. We're going to write fast clustering algorithms for optimizing these objectives, especially one in particular that I'll point out. And then finally, I want to show you how we can learn some cool things about both the theoretical and the practical performance of these objectives and algorithms on real data. The things that I want to offer you as takeaways from this talk are that first, approaching the topic of hypergraph modularity from a generative point of view can lead to both interpretable objective functions and fast algorithms. From a theoretical perspective, hypergraph algorithms can succeed where graph algorithms provably fail. And furthermore, the performance of hypergraph methods really depends on matching the structural assumptions of those methods to data. And a generative model helps us to think about that in a principled and quantitative way. Now, before I tell you the story that I hope will convince you of these messages, I want to highlight that there are other cool approaches to modularity in hypergraphs. So there's a paper by Kaminsky and collaborators in PLOS ONE, clustering via hypergraph modularity. This paper defines modularity by a comparison to a null random hypergraph in much the same way that the modularity objective was originally introduced for graphs. We're going to derive their version of modularity as a special case, and we're also going to derive some extra resolution parameters that make it much more flexible for application on real data. There's also a paper that I really like by Trun Kumar and collaborators, Hypergraph clustering by iteratively reweighted modularity maximization. That's in applied network science, just came out. This approach combines graph modularity to do the clustering, but it does it over and over again with an adaptive penalty that punishes so-called imbalanced hyperedge splits. I really like this. It seems to work well on hypergraphs of pretty nice size and with pretty good results. It doesn't, as far as I know, this approach isn't directly connected to a generative model. So that's a little bit more what I'm excited about is the generative approach. But there are already 2 great papers handling this topic from different perspectives. Sidebar, this is what I think is really rewarding and interesting about working in hypergraphs right now, is that there are usually multiple good, productive, and engaging generalizations of concepts from our graph and network science toolbox to the space of hypergraphs. So there's room for lots of different approaches and lots of different generalizations to all coexist on these topics. Okay, so now I'd like to jump in and work through this derivation with you, and then show some of what we can do with the results. So we're going to derive a hypergraph modularity objective. Before we do, a quick review of an important paper on this topic for the case of graphs. The degree-corrected stochastic block model is a statistical model, a generative model of clustered graphs with heterogeneous degrees, where in order to determine the number of edges between 2 nodes, we pull from a Poisson distribution, where the parameter of this Poisson distribution is a function of the degree parameters, theta, of the 2 nodes I and j. So if theta is large, you'll see more edges on that corresponding node that controls the degree, as well as an affinity function, omega, that governs the connection rates between groups. So this works for the case of dyadic graphs. We're not at hypergraphs yet. We can use this to pull random samples of dyadic graphs that have heterogeneous degree distributions, as well as planted cluster structure. Now, a nice result about this is that modularity maximization, the modularity objective that I showed you earlier, approximates maximum likelihood inference in this generative model. So in particular, you can write out the log likelihood for this generative model, and then you can make an approximation, and this approximation is exact when all of the clusters have the same volume or sum of degrees. And in this approximation, you find that you get terms reflecting exactly the modularity objective, and then you get terms that do not depend on the node labels and can be ignored in the optimization problem. So there's this nice connection where we can view modularity maximization as an approximation of maximum likelihood inference in this degree-corrected stochastic block model. This observation really motivates our approach to the problem of deriving hypergraph modularity. So we propose a hypergraph degree-corrected stochastic block model, a bit of a mouthful. DCHSBM is what we usually call it. And in this model, we take the same ingredients that we had before. So we are going to look at a tuple R of nodes. This can be a tuple of any size. So we might say, okay, well, R contains nodes 3, 7, and 10. In order to determine the number of edges on this tuple R, we are going to sample from a Poisson distribution again, where we are going to consider 2 points. The first is the model's view of the expected degrees of the nodes, and these are again reflected in degree parameters. We just have now more than 2 of them to multiply together, but they play the same role. Second, we are going to have a generalized affinity function that we've called omega here. Omega is a function of the group labels of the nodes in this tuple R, and it governs the rates of connections between different groups. So omega might say, for example, well, there are more connections within groups than between groups. This model can generate hypergraphs with both heterogeneous node degrees and heterogeneous edge sizes, which is a little bit unusual, actually. A lot of extant generative models for hypergraphs work with uniform hypergraphs where all edges have the same size. So because a lot of the data sets that we really care about have edges of many different sizes, we felt it was really important to bring in a more flexible objective function in that way. So I want to briefly illustrate the affinity function so we can get some intuition here. So the affinity function omega governs connection rates between groups of nodes. So in an assortative model where we expect that connections will be dense within groups, we might say, okay, well, when all the nodes have the same label blue, omega is a little larger than in the case where maybe two of the nodes have the same label and one of them has a different one. That in turn might be larger than the case where all three nodes have different colors, et cetera. So this is a case where we're dealing with an edge of size 3. We actually make a further assumption on the affinity function for the purpose of tractability here, which is that we assume that the affinity function evaluated at a vector of labels is a function of the partition of that label vector. And what I mean by partition is you just count the sizes of each groups. This particular assumption implies that all the groups are statistically identical, conditioned on their degrees. Here's an example of computing the partition. So I take a label vector z sub r. It's on an edge of size 6, and I see, okay, there is 1 pink node, 3 blue nodes, and 2 yellow nodes. And so I forget what the actual colors are. I just remember, okay, I saw 3 of one, 2 of another one, and 1 finally of the third group. So I forget exactly what the colors are. I just remember the sizes of the groups involved. When you make this assumption, a benefit is that it turns out it's easy to perform maximum likelihood inference for the parameters theta and omega as well. So we can estimate theta. It turns out that setting theta equal to the observed degree will work just fine as an approximation. Similarly, setting omega equal to this somewhat more complicated fraction will work well. We count the number of hyperedges that have the specified partition, and then we divide that by this somewhat gnarly sum product here, where we take products over clusters of labels. So this approximation is exact, again, in the same case as before, actually, when all clusters have the same sum of degrees. So this gives us an approximate maximum likelihood framework for estimating these parameters. Of course, estimating the parameters theta and omega isn't really the hard part here. The hard part is optimizing over the label vector z. And this is where we come to a modularity type objective. So the big reveal here is that we can approximate the log likelihood, again, by first some constants that are, some terms that are constant with respect to the label vector, don't have to worry about them. And then additionally, this big sum up top that if you squint hard, bears some resemblance to the modularity functional for graphs. We sum over all the different ways to cut up a hyperedge. So we sum over the partitions P. And then we have a first term corresponding to a cut penalty. And the cut gives us the number of hyperedges that have the specified partition P. Then there's a second term where we have a volume penalty. And this again multiplies over the volumes of different clusters. And this is interesting because this term is actually partially independent of the actual edges. It depends only on the cluster labels. So as in the classical modularity framework, we end up balancing something that looks like a term that reflects the actual edges with a term that reflects something independent of the edges and can be viewed in one sense as a null model, or in a different way as just a term that falls out of a generative model for pulling random hypergraphs with the desired structure. So we call this function up top there a symmetric hypergraph modularity. This is a pretty natural generalization of the basic modularity function of the hypergraphs, and I'm going to make that a little bit more concrete shortly. This one, the fully general one up here, can be a little bit complicated, as it turns out the fact that we have a term depending on omega that multiplies both the first and second terms makes things a little bit grubbier mathematically here, but we can still work with this. I want to focus on a really special and important case of this setup. So suppose that you actually specialize omega even more. So this omega or affinity function is now going to take the following highly specialized form. It's only going to ask, does the edge consist of exactly one group? In other words, does the edge have homogeneous labels? Everyone has the same label. Or does the edge have 2 or more labels? So we call this the all or nothing affinity function, and it corresponds to the all or nothing modularity objective. Now, one thing about this omega function is that it can depend on the size of the edge. So we can say, okay, for each possible size of edge, I'm going to ask whether that edge has homogeneous labels. And then I'm going to give it a parameter or a value for the affinity function that depends on the edge size and whether the labels are homogeneous. If you do some algebra here, you can simplify the modularity objective considerably, and resulting in this expression we have in the gray box now. So we sum not over all the possible partitions, we actually sum only over possible edge sizes k. We count the number of homogeneous k edges, that's our cut term. We penalize that with a product over the volumes of the different, with a sum product over the volumes of different clusters. And then there are these two parameters here. So there's a gamma that is regulating the impact of this volume term. And then we have a beta, and this beta actually multiplies both terms. And that means that we can view beta as determining the overall importance of hyperedges of the specialized size. The derivation to get here from the previous slide follows directly that of Newman in his paper in 2016 in PRE on this topic. And the resulting modularity objective generalizes the objective of Kaminsky et al. In their recent paper that I mentioned earlier. An important point about these parameters, beta and gamma, is that they are interpretable and can be estimated from data. So the size parameter beta controls the importance of edge sizes. If, for example, you set beta 4 equals to 0, that says ignore hyperedges of size 4, they don't figure into the objective. And can tell you, okay, well, when you adaptively estimate these parameters, how important are edges of any given size in enforcing the given cluster structure. The resolution parameters gamma control the number of clusters. So these are exactly analogous to the resolution parameters that we saw earlier. Larger gamma means more clusters, and you can vary these independently according to the hyperedge size. Again, you don't have to set these a priori. You can estimate them from data in an expectation maximization type scheme. Okay, so how do we actually estimate some partitions on data sets? Well, Nate wrote this amazingly fast hypergraph Louvain algorithm that I'm so pleased with how this turned out. So in the hypergraph, sorry, I should pronounce correctly, Louvain. So in the hypergraph maximum likelihood Louvain, all nodes start in their own cluster. We're going to greedily agglomerate nodes in order to maximize the modularity objective. Then we're going to greedily agglomerate entire clusters of nodes to further maximize the modularity objective. We're going to estimate the parameters given by the affinity function and the degree parameters, and then we're going to repeat this for some specified number of times. You can do this for any assortative omega, so any omega function that encourages edges that are relatively more homogeneous. However, the math simplifications imply that you can do this for very large instances using the all or nothing omega due to some algebraic simplifications. So using Nate's fast all or nothing hypergraph Louvain code, we can actually retrieve correlated partitions on synthetic hypergraphs in a pretty difficult clustering regime. On hypergraphs of 1 million nodes, so we can do pretty practical large instances this way. Furthermore, the code that we've written here is just about as fast as the dyadic version that's usually based on projecting the hypergraph to a dyadic graph and then clustering that. We don't incur any major performance hits by instead operating on the hypergraph itself. Interestingly, there's this dashed gray line in the middle of the middle plot here. So this is actually the dashed gray line that we get from first running dyadic Louvain, so the very classical kind of Louvain algorithm, and then using that as a warm start to a hypergraph Louvain, which then refines the initial partition. So it looks like in some practical contexts, you can actually achieve substantially better results by combining these two methods. We think that's pretty interesting, and we'd love to see some folks who are kind of application oriented do some experiments about an understanding of why that works as well as it does. For the rest of this, we're going to be focusing on the pure hypergraph maximum likelihood Louvain algorithm, however. Okay, so I want to talk a bit about detectability thresholds, which are a theoretical topic that are very interesting to mathematicians like me. So detectability thresholds govern the information-theoretic limits in which graph clustering algorithms can succeed at all. So we did a little experiment on this where we wanted to see, well, are the detectability thresholds that constrain graph-based methods the same as the ones that constrain hypergraph-based methods? So here's what we did. We generated a whole bunch of random hypergraphs where we planted two communities or clusters, and then we said, okay, we're going to vary the rate of two edges or standard edges that go between clusters, as well as the rate of three edges that go between clusters. So for example, in the top right, we have a situation where both two edges and three edges tend to be within cluster. On the other hand, if you go over to the top left, that's a case where three edges are largely within cluster, but two edges usually go between clusters, and so on. So we get four kind of quadrants here where the different sizes of edges carry different kinds of information about the clusters in this random hypergraph. So one thing you can do with this is you can project this down. You can take the three edges and replace them with three cliques, and then do a dyadic method on that, classical graph Louvain. Another thing you can do is you can use hypergraph maximum likelihood Louvain that we've just proposed. And here's what comes out. So on the left, we have the result for doing graph Louvain. So we see that really the algorithm only succeeds in recovering partitions correlated with the planted ones when both P2, the rate of two edges within clusters, and P3, the rate of three edges within clusters, are reasonably high in combination. The dashed line that I've shown there, that's the theoretical limit. The fact that graph Louvain does not achieve the theoretical limit reflects the fact that it's not an optimal algorithm, provably. So it would be very interesting to look at the behavior of other algorithms that are provably optimal in this regard. On the right, I've shown the usage of hypergraph maximum likelihood Louvain for the same task. Here we can observe some dramatically different detectability regimes. So there are cases where the three edges tend to run between communities, but the hypergraph method is actually able to use that information separately, allowing it to detect the clusters based on that fact that the three edges are kind of anti-information in this sense. It's also able to detect in cases where two edges tend to run between communities. So overall here, in this case, the dashed lines correspond to the theoretical limits when one ignores one or both of the one of the edge sizes. So P2, for example, is the theoretical limit when one ignores edges of size 3. So we think there's a ton of really exciting work to be done here around this plot. This is purely an experimental result. But as a theorist, I'm really excited about this because I think characterizing the limits of detectability in hypergraph models with hypergraph algorithms, it looks really rich. It looks like there's a lot to explain here. And I'd really love to see future math work that can help us get a better grip on what we're seeing in these kinds of plots. Natural question. Okay, I've shown you some stuff on synthetic data of different kinds. I've tried to argue that one, this approach is pretty scalable, and two, there's some interesting qualitative differences in synthetic data that we might be able to learn more about from a theoretical perspective. Natural question, look, does it work on real data? So I'd like to share with you, to wrap up, a few of the experiments we've done on real data sets. So first we looked at school contact hypergraphs. So these are from the Sociopatterns project. There's an edge between a group of students if they were simultaneously in proximity and facing each other. So you think about, okay, there's a schoolyard, there's a group of 4 students, they're all talking to each other. We log an edge using these wearable sensors. So there are edges of sizes 2 through 5 in these two hypergraphs. We have one for a primary school and one for a high school. So when we compare Louvain algorithms on these data sets, we see some interesting patterns. So if we go for a relatively standard Louvain algorithm that only aims to maximize the classical modularity, we'll find that in both the primary school and the high school, we'll get some weird results where we've jumbled some of the clusters together. Looks like we're clearly achieving a partition that's correlated with ground truth, but it's not completely correct. If we check on a maximum likelihood variant of Louvain, where we try to maximize not the modularity itself, but actually the overall likelihood objective, we can do much better. So in this case, the Louvain algorithm will completely correctly characterize the primary school clusters, and it will get the high school clusters almost correct. On the other hand, if we retain the higher order information and don't project down into graph space, we actually use a hypergraph method, we'll find that we're able to perfectly classify both of these contact data sets. So we are able to avoid even the small errors that graph-based methods can make here. So this is a pretty promising result. We can use hypergraph clustering methods to exploit information that is not available to dyadic methods in something perhaps like the theoretical results we saw earlier. I'm going to skip this slide actually in the interest of time. So I want to show you a few more data sets as well. So that was a relatively small instance, the primary school and high school data sets. Those are a couple hundred nodes each. We have a few other instances that we tried as well. So in the Trivago Clicks network, edges are online browsing sessions on the website trivago.com. This is a travel website. And nodes are the hotels that users clicked on. So an edge joins a number of hotels that a user was in some sense simultaneously interested in. In this case, the node labels are the countries in which those hotels are located. In the Walmart trips dataset, an edge is a shopping trip, and nodes are items that were co-purchased in the same shopping trip. And the node labels are product categories, like groceries or outdoor gear or toys, for example. And then finally, we have two data sets from the US Congress. So in this case, edges are bills in recent US Congresses, nodes are legislators, and the node labels are party identifications for the legislators. So we tried our algorithms on each of these data sets. Oh, and I'll show you a bit about the size, sorry. So these data sets are somewhat larger than the primary school data sets. So the full Trivago data set has about 170,000 nodes. Walmart has just under 90,000 nodes. House Bills has about 1,000 nodes. And the Senate bills has about 3,000 nodes. Now, I will say that for Trivago and Walmart, these are very sparse data sets, and in particular, they have a lot of singletons. So what we did is we took progressively denser cores of the data sets and then studied the behavior of these algorithms. So here's what we found. There's a lot to take in here. The red line is the behavior of our hypergraph maximum likelihood Louvain. The gray lines are two versions of graph maximum likelihood Louvain, so just using dyadic information based on projections, one of which has been normalized so that the degrees of nodes stay the same in the projected graph. The other one is not normalized. So what we observe here is that there's no consistent best algorithm among these three on these data sets. So in the Trivago data set, even as we take progressively denser cores, hypergraph maximum likelihood Louvain does substantially better than either of the two dyadic methods. However, when we look at other data sets, when we look at Walmart, for example, in the 2-core of Walmart, hypergraph maximum likelihood Louvain does not do very well at all. Both of the dyadic methods are better. And then as we densify the Walmart data set, we see, okay, well, it tends to do about as well, maybe a little bit worse than the normalized version of graph maximum likelihood Louvain. In House Bills, hypergraph maximum likelihood Louvain doesn't really seem to get much of a correlated partition at all, whereas graph-based maximum likelihood Louvain can. It's the other graph-based maximum likelihood approach, however. And then in Senate bills, we see, okay, well, the hypergraph approach can recover a partition correlated with the ground truth, but not one that's really as good as the graph maximum likelihood approach, again, the unnormalized variant. So there are different data sets here, each with different kinds of higher order structure, and it's not guaranteed that any given higher order clustering algorithm is going to do well across data sets. Now, the benefit of working in a generative paradigm is that we can actually understand this kind of behavior in a principled way. So I'm going to ask you to remember that Walmart and House Bills were the cases where the algorithm really was clearly outperformed by one or more dyadic methods in a strong way. Because we're working in a generative framework, we can assign likelihoods and penalized likelihoods to different data sets. And so we can actually check, for example, something like a Bayesian information criterion. So a Bayesian information criterion lets us do model selection. We can compare different choices of the affinity function and see how they do. So in this table, I compare two different choices of the affinity function for each of the data sets. The first choice is the all or nothing affinity function that underlies our fast hypergraph maximum likelihood Louvain. In the second column, I also show a pairwise affinity function. This is an affinity function that uses only information about dyadic connections between pairs of nodes, so it does not make as much use of higher order information. And then we compute the Bayesian information criterion. So a lower number is better here. And indeed, what we can see is that in certain of these data sets, particularly the ones where hypergraph maximum likelihood Louvain performed very well, the all or nothing affinity function is actually preferred by the data. It has a lower Bayesian information criterion. Whereas in Walmart purchases and house bills, the data sets where we performed less well, the pairwise affinity function is actually preferred. So when we look at these results and we say, hey, the hypergraph algorithm is doing well here and doing less well here, the benefit of the generative paradigm is that we can really say, hey, this is because actually the underlying assumption of the all or nothing affinity function is not a good match to the data. This really highlights the importance of domain expertise and modeling thinking when doing hypergraph clustering. And so we think this is a really important point that we want to emphasize. We can reason in principled ways about the performance of our algorithm because we're working in a generative kind of approach. Okay, so I'm just about at time, so I'd like to wrap up. We learned, and I hope that you've learned as well, that a generative approach to hypergraph modularity can lead to interpretable objectives and fast algorithms. Hypergraph algorithms can succeed in information-theoretic regimes where graph algorithms necessarily fail. However, performance in practice depends on matching the structural assumptions of algorithms to data. There's still a ton to do here, and I really think that this is the first chapter, or maybe not the first chapter, it's the third or fourth chapter of a long story that has many more chapters, and maybe some of you will write them. So there are alternative inference frameworks for the generative model that we proposed, like Bayesian Monte Carlo, like belief propagation, or even other greedy heuristics. There might be faster algorithms for general affinity functions. Our algorithms can work for more general affinity functions, but they're fast specifically for the all or nothing variant. There is definitely room to improve there. I personally am really excited to get a mathematical understanding of the information-theoretic limits of hypergraph inference frameworks. And I'm sure that many of you in the audience have really cool ideas that you're already thinking of here. So please make something cool happen. So here's the preprint, generative hypergraph clustering from block models to modularity. Again, this is the team. I'd like to thank Nate. I'd like to thank Austin and our funders listed below. And finally, I'd like to thank everyone here for your time and attention. And if there is time, I'd love to take a few questions.
So thanks, Phil. So we have time for one or two quick questions.
Okay.
Yes, hi. Thanks for the amazing talk. I had a question on the definition of the modularity for hypergraphs. In that definition, the first term was the hyper edges that contained all the nodes inside one of the partitions, right?
Mm-hmm.
Does your generative model, is it capable of generating hypergraphs which could have like different number of nodes that different number of stubs that go into intra-partition hyper edges? For example, let's say there is 4 uniform hypergraph. And the number of stubs that go in cluster A and cluster B can be 1, 3, 2, 2, 3, 1. In case of graphs, it's like fixed 1, 1. But in case of hypergraphs, is your model capable of doing that?
Yeah, so the model is capable of generating hypergraphs with that structure. However, the inference algorithms in that case to actually learn the model will be substantially more complicated and definitely an area of active and planned work.
Okay, I see. And one
great question.
So does definition, is it equivalent to the definition for the graph if I put k equal to 2 here?
Yes, if you restrict k equal to 2 and you do some algebraic manipulations, you will get something that is proportional to the objective for graphs. I say proportional because I think, for example, that the traditional normalization by 1/2m that is often used is usually misleading, and so that won't be in there actually. But I think that's usually the wrong normalization anyway. But yes, you'll if you plug in k equals 2, you will recover something proportional to the classical graph objective.
Okay, thanks. That answers it.
Hello. Hello.
Hi, yes.
Hi. Hey Phil, this is Tarun. Thank you for this wonderful talk. So my question is on the applicability of hypergraph-based method. So in your case, hypergraph Louvain. So the method hypergraph Louvain is very inspiring. When we talked about results, then on some data sets, we saw that graph-based methods were outperforming the hypergraph-based method. And I have seen similar instances with my experiments as well. Ideally, it should not happen, right? So we are capturing more information when we are working with hypergraph-based methods. So what is your take on that? Why is it happening? So is there any noise in the higher order structures, or is there something that we should not have captured?
Yeah, so I think there are two reasons for this. Or two main reasons for this. So first of all, with hypergraph-based objectives like the one we have here, it's just the case that the objective landscape is more complicated. There are more local optima, more opportunities for an algorithm to get trapped. And so that can certainly happen. That said, I don't think that's the issue that's going on here. And I think the second point, which in my opinion is kind of more fundamental, is related to model specification. So when we consider hypergraph-based models, at least in the approach that we've proposed here, there are assumptions made, such as, for example, the all or nothing assumption about the structure of the hyperedges and how those depend on the node labels. These assumptions may not be good matches to the data, right? And so I think that what we're seeing here, for example, in the case of, for example, House bills and Senate bills, these two legislative networks. Well, what's going on there is that most bills in the US Congress, surprisingly enough, are actually sponsored by people of multiple parties. And so the all or nothing assumption is not really appropriate for that case. Similarly, for Walmart, I don't know how well this translates internationally, but no one goes to Walmart to just buy one kind of thing. You go to Walmart to buy like a little of everything. So it's not really the case that hyperedges should be expected to lie in the same cluster there. So we think this is just a case of model misspecification. Now, I think that I suspect that tractable like hypergraph clustering approaches are always going to require some kind of assumptions in order to be computable. And so this means that there's really a scientific question about matching those assumptions appropriately to your data set.
Mm-hmm. Yep. Okay. Yeah, that makes sense. Yep. Okay. Thank you.
Yeah.
Thank you.
Thanks for the great question.
Thanks a lot, Phil, for the wonderful presentation. So let's move on to the next talk. So the next